We've been told particles exist in many states until you measure them, or something like that. But that doesn't quite hold up, because the moment you ask what measurement actually is, everything starts to fall apart. Because when you actually look at it, nothing in the theory, quantum mechanics says, nothing in the theory clearly explains why one outcome appears and all the others disappear. So here's the real question. What actually forces reality to choose? Physics, Consciousness and Reality, Dickie Dredd and Nigel Adams. And this is part 8 in the video series, still on chapter 1, The Hard Science. Section 5 in the book, Wavefunction Collapse, Randomness, Models and Interpretations. One of the strangest corners of quantum mechanics is the issue of wavefunction collapse. According to the maths, the particle isn't in one place or state until you measure it. Before that, it's smeared out in a superposition of all the possibilities, described by a famous linear wave equation developed by Erwin Schrödinger. The wave function is the cloud of probabilities, describing this haze of maybes. It's not a wave in anything, it's a wave of probability, whatever that means. No one really knows yet. But the moment you observe, the wave function collapses into one outcome. An electron is here, not there. The cat is alive or dead, but not both alive and dead. This is the so-called measurement problem. What does it even mean to observe? Does the particle somehow know it's being watched? Is consciousness involved? Or is collapse just a convenient story we've invented to keep the maths in line with what we actually observe? For decades, most physicists sidestep this question with the old line, shut up and calculate. The equations work, the technology works. Don't poke at the philosophy. But that leaves a massive gap in our understanding. If collapse is real, what causes it? Some theories try to make collapse into a genuine physical process. These are called stochastic collapse models. In this view, particles don't need a conscious observer. Instead, the universe itself introduces tiny random jolts, spontaneous hits of noise that push the wave function into a definite state. For a single particle, the jolts are small, so the superposition can last. But for bigger objects, the randomness adds up quickly, forcing them to choose one reality. That's why we don't see chairs or people existing in multiple places at once. Then there's Roger Penrose, who proposes a link between collapse and gravity. Superpositions involving two different mass configurations would mean two competing curvatures of space-time. Penrose argues that such states can't last. Nature itself resolves the tension by collapsing the wave function. The larger the mass, the faster the collapse. For an electron, the superposition would linger. For a cat, it would vanish almost instantly. It's elegant but still unproven. Experiments are only just reaching the accuracy needed to test it. But not everyone thinks collapse even happens. Some say the whole idea is on the wrong track. Take the pilot wave theory, also called Bohmian mechanics, after David Bohm. Here, particles always have definite positions, guided by a hidden pilot wave. The wave spreads out according to quantum rules, but the particle rides a clear path, like a surfer on a wave. No collapse is needed. The uncertainty is just us not knowing the hidden details, or hidden variables as they're often called. Einstein wouldn't have liked that. Since he couldn't stand the idea of randomness at the heart of reality, God doesn't play with dice. The catch is the pilot wave theory makes the universe explicitly non-local, as stated in the last part when we discussed entanglement. That means particles can influence each other instantly across space. Experiments with entanglement suggest this might be true, unsettling as it is. Then there's the many worlds interpretation, pioneered by Hugh Everett and named by Bruce DeWitt. Instead of collapsing, the wave function just keeps evolving, splitting into branches. Every possible outcome happens, but in different universes, inaccessible to each other. You measure a particle, in one branch you see it here, in another version of it, you sees it there. A different version of you sees it there. Reality keeps forking endlessly. No collapse, no randomness, just branching universes stacking up with every quantum event. Some physicists love it because it keeps the maths clean. Others hate it because it explodes reality into an unfathomable multiverse. There are other views too. Cubism, for example, says the wave function isn't physical at all. It's just a tool for organising your personal expectations about outcomes. In this frame, quantum mechanics is less about the universe and more about the bets you place on your own observations. Neat but unsatisfying if you want an explanation of what's really happening. So where does that leave us? Quantum mechanics is the most accurate theory we've ever built. It underpins computers, lasers, semiconductors, MRI scanners, basically modern technology. But at the core, we're still in the dark about what the wave function represents, how the haze of possibilities becomes the single reality we experience. Do collapses actually happen, driven by randomness or gravity? Are particles secretly riding pilot waves with non-local connections pulling the strings? Do we live in an endlessly branching multiverse? Or is the whole debate misunderstanding because the wave function is nothing more than a clever piece of bookkeeping? Each interpretation is consistent with the maths. None has been decisively proven or disproven. All of them reshape reality in ways that feel bizarre and unintuitive. For now, we're left with a riddle. The equations tell us probabilities. The experiments confirm them. But the story of what's really going on under the hood, that remains one of the deepest mysteries in science. So what this section really shows is that we don't actually know what turns possibility into a single outcome. And if that's true, then reality might not be something that exists independently at all. Which means the problem isn't just how particles behave, it might be that we don't understand what real even means. And if that's the case, are we observing reality or are we creating it? Next up, still chapter 1, the hard sciences, we're going to summarise the standard model in part 6 of the book. Just some news on the book. I've submitted the drafts of the book and the cover, which has all been completed by Paul Garbutt, did the cover design, or rather Nigel did the cover design and Paul Garbutt helped us pull it into the right format. And now we're heading off to the press and getting a quote, and hopefully soon we will have a link. And there's also a website now for the Ocus Press, which I will release in the next video.